Today we'll start from page 199 about multiply BGT networks. Okay. In multiply BGT networks, we have many. First of all, why I need multiply BGT networks? See this graph. Let's discuss about this graph. Excuse me, focus with me. In this graph, as you see, we have two transistors. This is the first one, and this is the second one. So here, each transistor means stage. So we have stage 1, stage 2. Okay. Why I need two transistor, not one? This is for example, I need to I have here small current or small volt. I want to increase this one. Can I increase, for example, transistor, or for example, just transistor 1 with bit equal 1000? Yes, we can. But for this reason, we need special transistor and we need big transistor. And the most important thing, that's mean temperature. That means temperature will be very high for this transistor. So instead of using one transistor with bit 1000, I will use two transistor, transistor 1, transistor 2. And as you see later, beta here, beta total equal beta 1 multiply beta 2. That's mean here 100 with 100, for example, it's 10,000. It's bigger than the one transistor. So using multi-stage transistor just for increase beta. And I know beta is IC over IB. Output current over input. So conclusion, I need multi-stage to increase the amplifier. We can use one stage, but this one stage can produce a high level of temperature, and I need sometimes I need in all times, not sometimes, to usually to deal with this temperature to cool the transistor. And here's the big problem. So instead of using one, I will use 2, 3, 4 transistor to increase beta. This is now the definition of multiply BGT. Okay. Let's see models for this BGT, multiply networks. First one called RC coupling. RC coupling is the first model. What is RC coupling? Let's go to the diagram and see here. Again, we are talking in DC, not AC. See RC coupling, I have RC. So here between this is stage number 1 and here is stage number 2. As you know, this is voltage divider. I advised you yesterday, previous week, to return back to the electronics one. This is voltage divider. Stage 1. This is voltage divider. Stage 2. So between stage 1 and stage 2, there is, okay, give me this. There is capacitor. And between input or generator to first stage, we have also capacitor. Between the last one and output, we have capacitor. So for that reason, we said RC. So we have R and we have C. The job of this capacitor is isolate this stage from this stage. Isolate this stage from the output. Isolate input. So this is input from first stage. Why is isolate? As I told you before, if I draw the V, just VC, VCB مثلا IC. This is the output character if you remember. So I want to work in this region, this area, in active region. So if there is any load from the, for example, I'm talking about this one, PCB1. If there is no this capacitor or this capacitor, what will do? Maybe this point will shift to here. Okay, what does that mean? Again, this is saturation. So maybe my point will move from active region to saturation region. For that reason, my transistor doesn't work. So idea to why we have this capacitor is to keep my working point Q1 and Q2 on the active region. That means Q1 or stage 1 will not affect for stage 2, and stage 2 will not affect for stage 1. Same thing, generator will not affect on active region or the Q point for stage 1. And if I have here any load, this load will not affect for Q2 in stage number 2. For that reason, I'm using here this capacitor. What's the name? CC, coupled capacitor. That means connect this with this. Again, this is for DC. As you know from circuit theory, XC is 1 over 2B if C. And if here is 0, that means XC here is infinity. Because this is DC current or voltage. Any question for this? Is it clear? Okay. Now, how we can deal with two stages like this? I will separate each stage alone. That means stage 1, stage 2, stage 1, stage 2. That's mean this capacitor cut each stage alone. And you can calculate VCIC for each stage alone separate. Is it clear for you? Okay, can I connect voltage divider with, for example, common base? Yes. Can I connect voltage divider with common emitter, for example, fixed bias? Yes. I can connect any model with any model, but I must use capacitor between them. And see this one, I want to show something very important. See, this capacitor is chemical capacitor. See this? You know, for capacitors, we have many kind. We have ceramic capacitor, we have chemical capacitor. See, this one is chemical capacitor. So this is positive. This is negative. Is it clear? Any question for this? Any question? No. No. Another model that we have to study, and inshallah next year we'll find in the lab, circuit called Darlington. Darlington actually is a circuit like transistor, exactly like transistor, but in this one we have two transistors inside one bucket. Two transistors inside one bucket. Okay, how we can deal with these transistors? Let's see here. So in these transistors, I will connect. Okay, this big one. Emitter for 1 to the base for 2. I will connect emitter for 1 with base for 2. So this is Darlington. In Darlington, I will connect emitter 1 with another one of 2, base of 2. Okay. And output, as you see here, will be from this point, from emitter 2. So Darlington, not like normal circuit. No, I will connect here, this point, C1 with P2, and output will be from E1 with E2. And I will connect now, see this collector together, C1 with C2. So again, what about Darlington? In Darlington, I will connect collector base with emitter, and I will take out from emitter and collectors. I will connect the collectors together. How can I calculate beta total or beta Darlington here? Beta Darlington here, in your book you can find the steps. IB equal IE1, so IE1 is beta plus 1 IB1. Then we'll calculate here, you can find some mathematical. I need this. In Darlington, B Darlington or B total, it is beta 1 multiply beta 2. Beta 1 multiply beta 2, then you can calculate or find IB1, VBE1, and IB1 directly from the formula. It's easy. But I need to focus on this. Beta D is beta Darlington is multiply beta 1 with beta 2. So if beta 1 here is 100, if beta 2 also is 100, beta total is 10,000. Again, beta without unitless. So C Darlington is very important and gives to me a lot of amplifier. Then you can calculate here VCE1, VCO directly. We have also many kinds of transistors like cascade, but I need from this one to focus about RC coupling and Darlington. Here, Darlington, how we can calculate VBED, IB1, IC2, you have to read at your home. It's direct implement for Darlington. Cascade is cancelled in exam, so we don't need cascade and after that. But ideally in cascade, see here, we don't use, for example, to connect this base together and output from B here. Also, we have another one, for example, push-pull, like for example, like this one, feedback amplifier, DC, for example, another one. Here we have direct coupled. So we have many kinds of models. I need just two models in exam: RC couple and Darlington couple for final exam. Okay, in your book, if I will return back to this, go to the end of your book. Okay, here. This question is important. You have to solve at your home. For example, for RC coupled amplifier and determined in 4141, this figure, calculate VB, VC, VE for each transistor. This is voltage divider. So you have to solve for voltage divider. Then I have calculate the current IB, IC, and IE for each transistor. So here you have two examples, not one. And you have to, again, don't forget DC. C with DC is DCs, capacitors. With DC is open circuit. Don't forget this. So we'll cancel this, cancel this, cancel this, cancel this, cancel this. So we have two stages. First stage, second stage. So you have to solve as two stages. Second question that you have to solve at your home. For Darlington amplifier, this Darlington, you have to calculate beta D, base current of each transistor, collector current for each transistor, and voltage VC1, VC2, VE1, and VE2 for Darlington. So at home, you have to solve question number 45 and question number 46. Is it clear? Yeah. Current mirror is cancelled. You don't need current mirror. Current source circuit also cancelled. BMB transistor is cancelled. We will go to something very, very, very important, transistor switching network. Transistor switching network. In transistor switching network, I will make something. Okay. I will open painter. Okay, where is it? Here. I didn't find just a minute to find this one. Okay. Keep eye with me, excuse me. Yeah, your eyes, keep your eyes with me. I will take this cut. So where is it? Doesn't work. Okay, work. Copy to printer. Paste. This is the first one. Okay. In transistors, as I told you before, we have three regions, if you remember. So this region is active region, cut-off region, just going to work. Just a minute. Okay. In transistor, if you remember this, we have three regions. Cut-off region, saturation region, active region. And when we studied the transistor models, bias and self-bias and the voltage divider, I told you we cannot use this region. This active region or linear region for amplifier. Amplifier means here, see my hand. If I draw the relationship between IC and IB, see, IB increase, IC increase, IB increase, IC increase, until a critical point, this point. This is called IB max. After that, IB increase, IC will be constant. So this area called saturation. It's not in your book. This area is active. And here is beta. IC equal beta IB, this area. So if I want my transistor to work in active region or as amplifier, I must work in active region. If I want my transistor to work in saturation, it should be more than IB max. So IB increase, as you see, but IC is constant, no change. For that reason, we said it is saturation. This is very important. Keep in your mind. Okay. Now, why is this? Because in transistors, just a minute, cancel this. Thank you so much. We have, okay, again, what about here? Two models. These models are this model that we talked before. RC, RB, VO. This is transistor models. Here. This one, as you see here, in this, I will connect RB to VCC, and VCC is DC voltage or constant. Constant. Here, no. This input is not constant. So the main difference between using transistor as amplifier, here amplifier, here saturation, is how can I connect the input to the transistor? See in this one, VCC connect to the base. Here I will use not VCC, I will use pulse or any signal. This is the one, first thing. So this one I will use amplifier, here I will use as switch. Switch mean, if I return back to the graph, see this is VCB, IC, and this is the output. Here I gonna use two regions, this region and this regions. So in amplifier, I need one region, active region. In switch, I need two regions, saturation here, or sometimes I will use one or one here, cutoff or off or zero. Can use this, we can use this. So in active, I need just one region, active region, amplifier. In switch, I need two regions, on and off. Is it clear or repeat? Repeat or clear for you? Okay. Now, how how we start with this. Okay, I will return back to this and this. Again, let's talk about mathematical things, so physical things. Then after that, we'll talk about mathematical things. For physical, here if I have, for example, here, IB equal 1 microampere, IC will be, for example, bit IB multiply beta. That's mean, for example, 1 microampere multiply 100. That's mean 100 microampere. Finished. Here, no. How we can handle this? Here we don't have amplifier, by the way. Here we don't have amplifier. Here, see, I have, ignore this cancel. I will start from here. I will start from this point. This point. See, here I have 5 volt. I will see the output 5 volt here. See, and this is my transistor. I have here 5 volt here. If I return them back to this graph, previous graph, VCB, I, C, and this is the graph. In saturation, here, and this is cut off. See, what about IC? In saturation, IC equal 0. From this graph. And in cutoff, it's equal VCB equal 0. Okay, good job. Now, IC equal 0. IC equal 0. That's mean, let's check. Here I have 5 volt. What about this transistor? How this transistor will work like? IC is 0. That's mean no current here. IC equals 0. Let's focus about IC 0. That means no current. That's mean if you want, this one is off. What that mean? IC here from up is 0. I will redraw again to explain again for you. Here, see, this is 1 point, second point. So IC is 0. So I will connect this point to the ground. Because here, this area is 0, doesn't work. So I will connect this to the ground. So V out will be 0. Got it or repeat? Repeat. Focus with me, excuse me. See here. I have transistor, 3 points, up, down, ground. Here RC, VCC. Excuse me for this. If I have 5 volt, 5 volt, that means saturation. Saturation, that means IC 0. IC here is 0. That means this part doesn't work. So what about I will connect this VCC to the ground. So if I have on, I will got off. 5, let's say 1 or on. That means I have volt, but see the output, there is no volt. Got it or repeat? Got it or repeat? So if I have 1, output will be 0. Why? Because IC is 0 from this graph. See here again, I have one here, that means saturation. IC is 0, no current here. That's when I connect, I will drop this one to the ground. Now another case, cancel this, and let's return back the same graph. Let's study the second case. Now I am working here in off. Again here off or 0 volt. 0 volt here. 0 volt, that means VBE equal 0 equal VCB 0. So again we have 3 points, ground, resistor, then VCC. And this is the output, the output. Okay, VCB equal 0. Where is VCB? This is C, this is B. So what about, I will connect this here and I will make this short circuit. VCB here, CB equals 0. Okay. In VCB equals 0, just a minute. In VCB here equals 0, that's mean I will connect VCB here equals 0, this area. That means transistor doesn't work, sorry. Transistor doesn't work. This is on. Off, that means VCB is off. Transistor doesn't work. So I will connect VO to the VCC. And this is. So repeat. 5 volt saturation, 0 volt cut off. 5 volt saturation, I will connect transistor to the ground. So here is 0. Opposite case, 0 here, that means transistor doesn't work. I will connect V out to the VCC. Got it? Is it clear for you? Okay. If I return back to your book, this, excuse me. In your book, this is the cases in your book. Short, that's mean IC equals 0, short circuit. And this is cut off, that's mean open circuit and transistor doesn't work. Now, mathematical things. How we start to solve this one as mathematical things. For mathematical, we will start from, okay, return back to the, here. Again, this. Yeah. If I draw again the normal circuit, amplifier circuit, RC, RB, VCC, and the ground. If I want to solve this circuit, I will start from input. I will write IB equal VCC minus VBE over RB, IC equal beta IB, then VCB equal VCC minus IC RC. So I started from input to the output. Okay, here I have something very important. I'm working in active region. I will draw again this graph. Don't forget this. This is IC with IB. IB increase, IC increase, and this point. So for active, I'm working here. So I can apply this formula. But after this point called IB max, Here's saturation. I cannot apply this formula. Saturate. So how I can start to solve this example? I will start from out to in. From out, I need to determine this formula. I want to know IB max. So if I want to work, see this point, see my hand. If I want to work in active, IB should be less than IB max. So it is active. If I want to work with switch, I need IB should be bigger than IB max. So first of all, I want to calculate this IB max. So I will start from int IC equal VCC minus VCE saturation over RC from the same formula. VCE saturation, if you return back to this graph, where's this graph? I will draw again here. Saturation here this point. Again, don't forget this is IC with VCE saturation. VCE saturation is very small, so I can cancel this VCE saturation. I can say VCE saturation almost zero. VCE saturation in our book, sat is 0. So I can cancel this one. In another book, they will write VCE saturation equals 0.2 volt. But in our book, we used VCE saturation equal 0. So we don't have VCE saturation, just I have this formula. I will calculate IC from this formula. Then I have IC. I know this formula. I want to calculate IB max. IB max is the last point from active and first point from saturation. So IB max is the last point from active and the first point of saturation. So I will calculate IB max is IC over beta. Okay, I will calculate IB max in this case. I will know now IB max. This is from out. This is first. Second thing, I will return back to the input. See here, Arkadaşlar, take care. Here 5 volt and here is 5 volt. This example is not, sorry, obvious example. Why? Because this is VI, this is VCC. In our book, they made 5, but sometimes this is 10, this is 5. So here VI, here VCC, take care about this. Continue. I calculate IB max. Now I will calculate IB. IB here is VCC minus VCE, BBA, sorry, over RB from the input. Good. Now I will compare IB with IB max. If I need IB bigger than IB max, then we are working in saturation. So here we have two cases. First of all, I will calculate IB max from the output. Then I will return back to the input. I will calculate IB. And IB, if I want to work in saturation, I will take benefit from something. That means last point, end point of active region will be the first point of saturation. Okay, so for that reason, I can calculate IB max, then IB should be bigger than IB max. Got it? A little bit complicated. Is it clear for you? Okay. Now let's continue in our book to finish this idea. See here, I calculate here IC saturation. Here in our book, they said IC saturation. As you see, there is no VCE. So VCE is 0. Some boxes or other books they can use 0, 2 or 0, 1, but in our books they cancel. Okay, then I will calculate IB max, and I told you why. IB max, IC saturation over beta DC. Then I will calculate IB. See, this is IB and this is IB max. IB should be bigger than IB max. I explained you why this is this point IB max. So to work in saturation, IB, this is IB, should be bigger than IB max. I will calculate this one, and I will calculate after that IC. So for example, see here, IB is 36. IB max in our book is 48.8 micro. IB bigger than IB max, yes, so we are working in saturation region. Got it? In your example at your book, they ask me design. What design? I want to find now this, for example, here design for this one. Calculate IB max and yes, and IB, compare IB with IB max. Now let's take this example. Determine RB RC for transistor inverter. If I gonna use transistor as switch, it's inverter. That's mean flip 0 to 1, 1 to 0. So this is, we can say it's inverter. Inverter. So if it's on, will be off. I'm gonna use now on of that like digital logic. Next year, this is on. So this is off. This is off. Now this is on. This is called in English inverter. Okay, here we have another thing, HFE. What is HFE? HFE, and this is capital, equal beta DC and 250. So we have model called, inshallah we'll study later, it's called hybrid model, and F capital, E capital, that's mean DC. This equal this. Beta is here normal model, H is called hybrid model. We will study this hybrid model later about how we can do this one. Anyway, HFE is beta DC. Take care about capital with capital. Now let's go on. He asked me design. He gives to me IC saturation 10 milliampere, and I have also beta. I will start to find RC directly. I know that's mean IC equal VCC over RC. So RC equal VCC over IC saturation. Directly you can find the number. So RC here is 1 kilo ampere. Now I want to find RB. We know that's mean IB, it's VCC minus VBE over RB. So RB here it is VCC minus VBE over IB. But IB, which IB? IB here should be bigger than IB max because I want to work in saturation. Good. Continue. In your book, I calculate IC saturation over beta. This is IB max. This is IB max. Add this to your book, IB max. Now, trillion line under this one, choosing. It's choosing. How we can choose this one? Usually, for example, I have IB max. Again, return back to this graph. This is IB max. I need IB bigger than IB max. I need IB bigger than IB max. So usually, for example, I will multiply 20%. I'm not working here. I will not work here. I will work here, this area. So there is a guard. This area is a protecting area. About 20% from this one. So 20% multiply IB max. يعني if I have 40 microampere, I will multiply with 120. So almost, let's use calculator to find the result. Where's the calculator here? Okay, up, excuse me. For example, 40 multiply 120, it is over 100. 48. Here we used more. For example, now 60 divide 40, I guess 20%. 1.5 more, 150. Here we used 950, more than 50% increase. Anyway, here in this example, we used not 20, we used in our example here 50%. Choose 160 milliampere. That means here I'm gonna work here, not here, here. This point from here to here, it is 50% increase. Anyway, continue. I will find IB. It is here. See, VI. In amplifier, it is VCC. Here it is VI. Compare. This is for amplifier. Here for switch. Take care. Here we have VI. In amplifier, I have VCC. Okay, continue. IB VI over 0.7. Okay, I have VI, I can find the result. But take care about this one. They said to me 155 kilo ohm. Okay, it's correct. But here we have something, etc. Take care. Choosing RB 150 kilo ohm for standard value. For standard value, I need standard value. So I will gonna use the standard value, RB, and I have now 62 microampere. It's enough, not enough. I will compare, again, return to this graph. 62 microampere with 40 microampere. Bigger, yes, bigger, so it's correct. So after it changed standard value, by the way, standard values is, for example, here 100 kilo ohm, 150 kilo ohm, 200 kilo ohm, like this. For that reason, 150 is near to 150. Let's guess that I have 190, so it's near to 200 kilo ohm. That's the idea. Standard, that means 100, 150, 200, 250, and so on. So if I shift to the standard value, after that you have to work with check this value if it's correct or not correct. Here again I selected 62, so 62 is bigger than IB max. That means that my values are correct. Got it, the idea for this? Is it easy or hard? Inas, Abdurrahman, Jan, who is me also. Do you have any question about this? A little bit hard. Yeah, I agree with you, If. Agree with you. Now, this is the last thing for this chapter. This is cancelled. All of these are cancelled. Troubleshooting. Next year, inshallah, we'll study how to measure transistor in the lab. So let's go directly to the examples. This is 4617, 418, 419. It's cancelled. Here we have in your book summary. You can use the summary. And you can find the formula that we used, for example, for this one. Let's go to the examples and your book. And for transistor switching network, you have 3 questions, 57, 58, just 2 questions, not 3. So I will read the questions. Use characters of figure 41201. Determine the appearance of the output waveform for network. This is at here, it's easy question. Now, see here, design a transistor inverter. This question came of figure, this figure. Operate with saturation current. So I have IC current using a transistor with beta. So I have beta. He gives to me IB equal 100 of IB max. I explained. So here, if I want to design, I will write IB equal 120 from IB max. So you have to calculate IB max. It is IC saturation, here 8, over beta given. Then calculate IB max, then calculate IB. Then RB is VI minus VBE over IB. IB here from this, you will put here. Okay, I have input here 5 volt 07 silicon over IB, and you have to go to standard resistor value. Okay, you have these 2 questions you have to solve, and you can send me the result, or you can find the result on the internet about this question, up to you. Any question for this? Next week we'll start chapter number 5 about BJT AC transistor. It's very important, a little bit hard. So as you are going very fastly. Today we finished almost, I guess, 40 pages, something like this. I canceled something because it's a repeat or something important, very things for us. Yeah. What we did study, or what we have studied today, we studied 2 things. We studied, first of all, BJT amplifier. And we studied in BJT amplifier RC coupled. You have a question in your book you have to solve. And we studied also Darlington circuit. And inshallah next year also we have in our lab Darlington. So you will find on the kit. Then we studied also using transistor as a switch on off 0 1. And what is the difference between using transistor as active region and saturation and cutoff region for this one, and how we can solve this example, Excuse me, repeat this again to understand how we can solve switch, because a little bit hard, you have to understand this one. If you have any question, you can email me, or you can come to my office if you want. You are here, but email me before coming. Have a nice day. Any question else?